good afternoon, everyone. My name is Mridul Anjane. I'm an assistant professor in the Department of Computer Science at Rutgers University. And today I'll be presenting our work on progressive polynomial approximations for correctly rounded math libraries. This is joint work done in collaboration with my colleagues, Santosh Nagrakate and Jaylin. So why should we care about math libraries? Well, everyone uses math libraries. Now, mainstream math libraries produce wrong results, and correct results are important for portability and reproducibility of science. Now, there have been several works on generating correctly rounded math libraries. Through the RLIBM project, we have been making a case for generating polynomial approximations that directly approximate the correctly rounded result of f of x. And we achieve this by formulating the problem of generating this polynomial as an instance of linear programming. Using this technique, we were successful in generating several correctly rounded elementary functions for the 32-bit float type with the default floating point rounding mode. But now, everyone is designing their own representations, such as bfloat16 from Google and TensorFloat32 from NVIDIA. Additionally, people are using different rounding modes, such as the round to zero mode, for efficient hardware implementations. So our goal now is to produce correctly rounded results for all these representations and rounding modes, not just for the float type. Generating an implementation for each representation and rounding mode would be quite cumbersome. For example, the 4 representations shown here, along with the 5 rounding modes in the IEEE standard, would lead to 20 implementations per elementary function. So instead, RLIBM-All proposes a technique to generate a single implementation that produces correct results for all of these representations and rounding modes. The key insight here is to generate one single polynomial approximation for the 34-bit floating point representation using the round to odd mode, which is a non-standard rounding mode. While this method is very effective, its main limitation is that the same polynomial is used by all representations. So each representation pays the price for the largest one. The goal of this paper was to create polynomial approximations that give progressive performance. And that means that lower bit width representations are faster to evaluate than larger bit width representations. For example, consider the rounding intervals for bfloat16. And suppose we fit a polynomial p1x to these intervals. Since the rounding intervals are large, this polynomial is of low degree. Now consider the rounding intervals for TensorFloat32, which is a strict superset of bfloat16. That means every bfloat16 input is also a TensorFloat32 input, but there are other inputs as well. These intervals are somewhat smaller, so the fitted polynomial p2x has more terms and also takes more time to evaluate. Now consider the rounding intervals for the 32-bit floating point type, which is a strict superset of TensorFloat32. These rounding intervals are even smaller, so the fitted polynomial p3x is even larger, requiring even more time to evaluate. The benefit of progressive polynomials is that lower bit width representations share the same lower order terms as in the polynomial as the larger bit width representations. This makes them faster to evaluate and also allows for code reusability. The key challenge is that lower bit width representations give rise to many more constraints, which is beyond the reach of standard solvers for linear programs. Our key insight is that the problem of polynomial generation is a linear programming problem of small dimensions. And I'll talk more about that in just a bit. But the nutshell version is that this means that there are many more constraints than the number of variables in the system. Using this idea, we designed a fast randomized solver for linear programs with billions of constraints and implemented it in RLIBM-PROG, a math library that not only produces correctly rounded results for multiple representations and all standard rounding modes, but that is also faster than all mainstream math libraries. So before I describe our new technique, let me start out by providing some background on what a correctly rounded math library is and how our previous RLIBM technique generated correctly rounded elementary functions. Consider the real number line and adjacent 32-bit float values. The exact result of most elementary functions, such as log2 of x, cannot be exactly represented in floats and needs to be rounded to a float value using a rounding mode. This result, v2, is then called the correctly rounded result of log2 of x in float. An elementary function that produces correctly rounded results for all inputs is called a correctly rounded elementary function, and a math library of correctly rounded elementary functions is called a correctly rounded math library. Quite a mouthful. In contrast to previous approaches that try to approximate the real value of log2 of x, in the RLIBM project, we generate a polynomial that directly approximates the correctly rounded result of log2 of x. And the intuition is that there is a range of values near the correctly rounded result known as the rounding interval, where all values in the interval round to the correctly rounded result. And it suffices for the polynomial to produce any value in this interval to produce the correctly rounded result. So how does the RLIBM approach generate this polynomial? First, for each input, we compute the correctly rounded result of f of x using an oracle like the MPFR math library. Then, for each correctly rounded result, we compute the rounding interval. These rounding intervals define linear constraints on the output of the polynomial we wish to generate. So we encode these constraints into a system of linear inequalities and use an LP solver to generate a polynomial that satisfies all the constraints. This polynomial guarantees to produce the correctly rounded result of f of x for the one chosen representation and rounding mode. And the latest result of the RLIBM project, called RLIBM-All, produces correct results for representations with up to n bits by generating polynomials for the n plus 2-bit representation with the round to odd rounding mode. The main limitation of RLIBM-All, as I mentioned earlier, is that the same polynomial is used by all representations. So all representations pay the price for the largest one. So our goal was to design polynomials that give progressive performance. That means lower bit representations use only the first few terms during polynomial evaluation, making them faster to evaluate than larger bit width representations. The main challenge this poses is that lower bit width representations give rise to many more constraints, potentially billions of constraints. And this is beyond the reach of standard solvers for linear programs. Our key insight is that the problem of polynomial generation is a linear program of low dimensions, and that means that the matrix of constraints is a tall matrix. To solve the low-dimensional linear program with billions of constraints, we designed a randomized algorithm that is inspired by the seminal work of Clarkson. To understand how it works, consider a set of constraints as shown here. Initially, each constraint is assigned the same weight. We sample 6 k-squared constraints and solve a linear program with only these constraints to compute a k-term polynomial. Now in particular, note that 6 k-squared is a very small number compared to the potentially billions of constraints that we have in our system. In general, this polynomial also satisfies some of the unsampled constraints and violates the others. as we show here through our color scheme. We double the weight of the violated constraints and repeat the sampling process. Doubling the weight increases the probability of sampling the violated constraints in subsequent iterations. Here we show a new sample and the computed polynomial. This polynomial still violates 3 constraints. We double the weights of these 3 constraints and repeat the sampling process. Again, we show a new sample and the computed polynomial. This time, the polynomial satisfies all the constraints. Yay! So in our paper, we formally prove that when the system of constraints is full rank, then this randomized algorithm can compute a solution in 6k log of n iterations in expectation. And for other technical details, we refer you to our paper. Our prototype implementation is called RLIBM-PROG. It produces correctly rounded results from 10 bits to 32-bit floating point types. It gives progressive performance with bfloat 16, TensorFloat 32, and the 32-bit floating point type. We achieve this by generating a progressive polynomial for the 34-bit floating point representation using the round to odd rounding mode. We compared RLIBM-PROG against CRLIBM, RLIBM-ALL, Intel's DoubleLIBM, and glibc's DoubleLIBM. RLIBM-PROG produces correctly rounded results for all full floating point representations from 10-bit to 32 bits for all rounding modes. Here we are only showing the results for the 32-bit floating point format with all standard rounding modes. In contrast, glibc's DoubleLIBM, Intel's DoubleLIBM, and CRLIBM produce incorrect results either with one of the rounding modes or they produce incorrect results for lower bit width representations. Now this happens because of double rounding errors. Similar to us, RLIBM-ALL also produces correct results for all functions. RLIBM-PROG functions are more efficient than all mainstream math libraries. Here we compare its performance to that of Intel's DoubleLIBM, where we compute the result in double and subsequently round it to the target representation. The blue bars show the performance for bfloat 16, where RLIBM-PROG is 74% faster on average because of smaller polynomials. The orange bars show the performance for TensorFloat 32, where RLIBM-PROG functions are 64% faster on average. The performance drops because of a slightly larger polynomial in comparison to that of bfloat 16, and that requires more time to evaluate. The green bars show the performance for the 32-bit float type, where RLIBM-PROG functions are 49% faster on average. In comparison to CRLIBM, that produces correctly rounded results for double precision, RLIBM-PROG is 123% faster on average for bfloat 16. It is 105% faster on average for TensorFloat 32 and 85% faster on average for the 32-bit float type. Finally, RLIBM-PROG functions are also memory efficient over RLIBM-ALL, sometimes leading to over 150x reduction in space. This was important for practical adoption. In particular, LLVM's math library has implementations for log-f, log2f, log10f, expf, and exp2f that have been built using RLIBM-PROG. So in conclusion, RLIBM-PROG produces correct results for multiple representations and multiple rounding modes. Computationally, we pay as we go, in the sense that lower bit width representations do not use all the terms required for larger bit width representations, leading to faster polynomial evaluation times. To handle the large number of constraints, we designed a fast randomized algorithm by recognizing that our problem is a linear program of small dimensions. The resulting polynomials are not only more efficient, but also have lower memory overhead. This has allowed 5 functions in LLVM's libc to adopt RLIBM's implementations. Now that we can produce correctly rounded results for 10-bit to 32-bit floating point representations for all rounding modes, perhaps it is time to revisit the IEEE floating point standard and make correctly rounded results mandatory rather than just a recommendation. And I see some cheers, so that's great. So thank you all for your time. RLIBM-PROG is available online, and we are continuing to improve our library. If you are curious, please give it a try.
So, two quick questions. 6K squared, is any reason for the 6? And then second question, the classic hardware solution to the analytic functions would use piecewise polynomial approximations. Is there any idea of doing like a RLIBM piecewise prog going forward to give even more performance?
Yes, so both are very good questions. So we show in our paper that for proving that this fast randomized algorithm will give us a single polynomial when the system is full rank, the 6 is required because of the constraint sampling lemma. And that says that if we sample more than 6K squared constraints, then we have at least half the probability of sampling one of the constraints that is part of the basis. The piecewise implementation is actually part of RLIBM-PROG for some functions that are not full rank. So when we cannot generate one single polynomial for the entire system, then we break it into few piecewise polynomials and use piecewise polynomials. So that's how we are competitive with RLIBM-all.
Yeah, very nice work. Maybe I missed it, but I was just wondering what are the constraints in the LP here?
So the constraints in the LP are basically for each input we want to produce the correctly rounded result. So
what's the domain?
Sorry.
Each input as in like.
So for each input x, we want to produce the correctly rounded result of f of x. And there are a set of results around the correctly rounded result where if we produce any of these results through the polynomial evaluation, then they will round to the correctly rounded result.
So when you say each input, is this like each possible value that the float can take?
Yes, each possible value, and there are 4 billion of these.
Thanks.
So very nice work. I was just wondering, like 5 of your implementations were adopted by LLVM. What about the others? Why not all of them? Because this looks terrific. So.
Yes, so that's a great question. So when we were doing this work, we were of the opinion that polynomials generated by Solia were solely of higher degree than ours. But then it was shown to us by the Solia folks that they can generate lower degree polynomials also. So not just for one floating point rounding mode, but for all floating point rounding modes. The theory is still lacking as to why that actually happens. And these are implementations that are given to them by several other folks. So there is some math that still needs to be worked out, it seems. And we are also working on some of the other functions, for example, trigonometric functions. And there is Rutgers student, Seyok, who has a poster describing some of our attempts to solve this problem.
Cool. Thanks so much. And yeah, let's thank Camille one more time.